Hello, today we're going to look at the double angle formulas, and they are on page 14 of your log tables. So we should have page 14 of our log tables open so that we can work through these as I go. So if sine of A is equal to 2 root 2 all over 3, what would be sine of 2A equal to? So this is what we mean by a double angle. We have 2A instead of just A for our angle. So we go to page 14 in our log tables, and we see if we have any relationships for sine 2A, and we do. Sine 2A is equal to 2 sine A cos A. So we have this relationship, and there might be other relationships available to us, but I'm particularly going to go with this one because I already have information about sine A. I know sine A is equal to 2 root 2 all over 3, and that's in the formula that I see for sine 2A. The other piece of information I need is cos of A. I know sine of A, but I don't know cos of A. And this is where we're going to use a kind of a model triangle that's quite important for being able to interpret this type of question where you're given cos of an angle or sine of an angle or tan of an angle is equal to a fraction, because we can construct what the other trigonometric functions would be if we know sine, cos, or tan is equal to a particular fraction. And that's because these things relate to the angles in a right angle triangle. So if I have an angle A in a right angle triangle, the sine of the angle is equal to the opposite over the hypotenuse. So the opposite is 2 root 2, the opposite side is 2 root 2, and the hypotenuse is 3. So if I wanted to know cos of A, I would just need to find this missing third side, but I know lots about right angle triangles. I know that if I have this as my side A, I know that 3 squared is equal to 2 root 2, all to be squared, plus A squared. And this is my adjacent side that I need, and I'm going to use Pythagoras to find my missing side. And this is quite a common trick that we can use if we're given a trigonometric function and we're given it equal to a fraction or given ratio. So when we do that out, we are going to find that A is equal to 1. So we all know how to get from this step to this step. We're just doing simple linear equations. So A is equal to 1. So cos of A would be equal to the adjacent over the hypotenuse would be equal to a third. So I now know the pieces of information I need for subbing into my formula for sine 2A. So sine 2A is equal to 2 times sine A is given to us, it's 2 root 2 all over 3. And cos of A is a third. So we multiply that out and we get 4 root 2 all over 9. And that's the job done. How did we approach this? We were given information about sine A. That allowed us to construct a model triangle to figure out what sine, cos, and tan of A would be. We were asked about sine 2A, so I go to page 14 of my log tables and I see what different tools are available to me. And I see that I have something about sine 2A that involves a sine A, so that's the version of it I'm going to use. And from there, I just substitute in and simplify. Now, our next style of problem involving the double angle formula is where the double angle is a little bit hidden. So if I'm asked for sine of 4A is equal to 4 times, show that sine of 4A is equal to 4 times all of this, I'm going to leave this complicated side alone. I could try and refactorize this if I was so inclined, and it is possible absolutely to do it that way. It tends to be easier to use the formulas, find the way to rearrange and get the formula like it is in the log tables. So if I have sine of 4A, I can break this up in a clever way so that I can use the double angle formula. There's more than one way to do this question, but I could rewrite it as sine of twice 2a. That would be the same as 4a. So this is twice the angle 2a, and I have a formula for that. It's on page 14 in my log tables. It's going to be 2 sine of 2a cos of 2a. And then I look to where I want to end up, and I see that I have a sine a cos a here, and I know that at sine of 2a it would be 2 sine a cos a. So this bit is going to become 2 sine a cos a again. So I am going to have that as 2 on 2 sine a cos a all times cos of 2a. And now we're pretty much where we need to. We just need to multiply our 2's together, and we get 4 sine of a cos of a cos of 2a. Now, these can be fairly straightforward to spot when you get used to the equations on page 14. There is, however, another way to do this style of question. If they ask you anything about sine or cosine, so sine or cosine of 2a, 3a, 4a, on up. We haven't covered the maths of it yet. We're going to do it in complex numbers. But if you're asked anything about showing that sine or cosine of multiple angles, multiple a's, is equal to something like this, another way to solve the problem is to use something called de Moivre's theorem, which you will do in complex numbers. So you would use de Moivre's theorem. And you can just have that as a note to yourself for right now, and we will come back to it when we have done complex numbers. Now, continuing on with another style of question, if I know that cos of 2a is equal to 5 over 13, and I'm asked what tan a is equal to, this is a very, very similar question to what we did for our first question here. We're looking for sine of 2a, so I wrote sine of 2a in terms of sine a, the thing that I had information about. In this case, we are going to do something very similar. I know I want to get an equation involving tan a, and I'm given information about cos of 2a. So I'm going to go to my log tables, page 14, and I'm going to look for any formulas that connect cos of 2a to tan a. And I'll see that I get cos of 2a is equal to 1 minus tan squared a all over 1 plus tan squared a. And I'm told in the question that that is equal to 5 over 13. So I now have an equation that only involves tan a's, so I'm going to be able to solve to find the values of tan a. This effectively just becomes a quadratic problem, even though the term that is squared looks an awful lot more complicated. This effectively will just behave like an x. You could rewrite this as a substitution: 1 minus x squared all over 1 plus x squared is equal to 5 all over 13, and solve for x. And if you're more comfortable with that, there's no problem with doing that. Rearranging this formula, as I say, this is really just solving a quadratic. When you rearrange the formula, you are going to end up with 13 minus 13 tan squared a is equal to 5 plus 5 tan squared a. Rearrange, and you will get 18 tan squared a is equal to 8. So tan squared A is equal to 8 over 18, which simplifies down to 4 over 9. If we take the square root of both sides, remember that tan can be positive or negative, so we have plus or minus in this particular case. We have to take the plus or minus situation. So we would end up with tan A could be equal to plus or minus 2/3. So those are my values for tan A. Having solved my quadratic equation, tan A could be equal to 2/3, or tan A could be equal to minus 2/3. And those are my two solutions. And that's what we need for now.